Hello everyone, welcome to Math with Allison. Today we're continuing the derivative series, so I got some requests, so we're going to do logarithmic differentiation, and we're going to apply that to L'Hopital's rule as well. So let's go ahead and dive into it. The question is, why would we even use this? So we're going to go through an example in order to see why. We want to go ahead and find the derivative of cosine of x to the power of x. So I'm just going to go ahead and rewrite this. I'm going to set it equal to y, and this is going to be cosine of x on the inside, and then we have that power of x on the outside. So here what I want you to notice is that we have a variable in the exponent. So whenever you see a variable in the exponent, we're going to use logarithmic differentiation because we want to get that variable out of the exponent. In order to get it out, we're going to take the natural log of both sides, so you'll see why. So the purpose of taking the natural log is to use the natural log rules, which tells us that we can take anything that's in the exponent and we can bring it to the front. So the purpose of doing this is now we can take the derivative. So I'm going to go ahead and take the derivative of both sides in terms of x. So here, when I take the derivative of the natural log of y, I do have to use implicit differentiation. So first, what happens is on the denominator, we have whatever is on the inside of the natural log. And in the numerator, we have that derivative. So the derivative of y in terms of x is just going to be y prime, right? So now we have y prime divided by y equals. And we can go ahead and set up product rules. So we have our first term is going to be x, and our second term is going to be the natural log of cosine of x. So let's go ahead and set up product rule. Okay, let's take these derivatives. So the f prime is just going to be 1, and then g prime is going to be a little bit more complicated. So like we said, whatever's inside the natural log goes on the bottom. So here we have cosine of x. And the numerator is going to be the derivative of that. So the derivative of cosine is going to be negative sine of x. And actually, we can go ahead and rewrite this as negative tangent of x. So let's go ahead and find the actual derivative. We're going to cross multiply. So here I'm going to multiply these together. We get the natural log of cosine of x. And then we're going to add the second term. But in our case, it's going to be negative. So this becomes minus x tangent of x. Okay, so remember what we're trying to solve for. We want to get this y prime all by itself. So in order to get it by itself, I'm going to go ahead and multiply over that y. Okay, so we have y prime all by itself, but we're actually not done yet because notice in here, we still have a y. I want everything in my solution to be in terms of x. So I'm going to replace y with what it was originally equal to. Here we have y equals cosine to the power of x. So I'll go ahead and replace that. And there we have our final solution. So the point of logarithmic differentiation is when we have a function raised to a variable. So we want to go ahead and get that variable out of the exponent so we can actually take the derivative. So here we have an application of limits, and we had a request. We want to evaluate the limit as x approaches 0 of tangent of pi over 4 plus x all to the power of 1 over x. So this is logarithmic differentiation kind of, but when we're working with L'Hopital's rule. So notice here, if I were to use direct substitution first, I have tangent of pi over 4 when I plug in x is equal to 0. This is approaching a value of 1. Now, when I approach 0 of 1 over x, this is approaching positive or negative infinity, right? It's approaching, I think that's mirrored correctly, two different infinities. So really, this is going to be 1 to the infinity, which this is a form of indeterminate form, but it's not the kind that we can use L'Hopital's on. In order to use L'Hopital's, we need it to be in 0 over 0 or infinity over infinity. So we want to make it look more like that. So what I'm going to do is the same process. I'm going to set this equal to y. And the purpose of setting it equal to y is just like in our example problem, I'm going to take the natural log of both sides. So here I'm going to pull the natural log inside of the limit, and here we get tangent of pi over 4 plus x to the power of 1 over x. And for the exact same reason, we are going to go ahead and take this power and we're going to bring it to the front. So we're very close. What we need this to look like is a fraction. It needs to be a quotient so we can apply L'Hopital's. So let's go ahead and make it a fraction. So in the numerator, we have that natural log of that whole thing. And in the denominator, we just have that value of x, right? Because we multiplied by 1 over x. So now let's go ahead and try direct substitution because we actually need to see the indeterminate form. So I'm just going to plug it into this right side. So we get the natural log of tangent of pi over 4 plus 0. So I'm just going to say pi over 4, and this is going to be divided by 0. We already know this is illegal, but we don't know if it's indeterminate form, so I'm going to keep solving. So here we have tangent of pi over 4 is equal to 1. This is still divided by 0. And natural log of 1 is actually equal to 0. So this is our indeterminate form, 0 over 0. So we can go ahead and apply L'Hopital's to this right side. So let's go ahead and set up the derivative of the numerator because we got a lot going on here. And we're going to do that by setting up chain rule. So I have the inside is equal to tangent of pi over 4 plus x. And I have the outside, g of u, is equal to the natural log of the inside. Okay, so u prime is going to be equal to the derivative of the outside, so secant squared at the inside. And this one's nice because when we multiply by the derivative of the inside, we're just multiplying by 1. The derivative of pi over 4 plus x is equal to 1. Now, g prime of u is going to be 1 over u. So when we set this up and we actually find the derivative, we have secant squared, and we're going to multiply that by g of prime of u, but we're going to go ahead and plug u back in. So u was equal to tangent of pi over 4 plus x. Okay, so we're in the simplifying process, so I'm going to go ahead and rewrite this. The secant squared is 1 over cosine squared. Whenever we have a lot of trig going on, I really suggest rewriting everything in terms of sine and cosine and simplifying that as much as you can. So 1 over tangent is just going to be tangent flipped. So I know tangent is equal to sine over cosine. And when we have 1 over that, we just flip the fraction. So that's going to be cosine over sine, everything at the inside. So here we can see that one of these cosines is going to cancel out. So we have 1 over cosine of pi over 4 plus x times sine of pi over 4 plus x. So I'm going to go ahead and erase all this and rewrite it back in the limit. So in the numerator, we got 1 over sine and 1 over cosine, which I can just rewrite as cosecant times secant. And the derivative of the denominator now is going to be the derivative of x, which is just 1. So if you don't like cosecant and secant, you can rewrite that in terms of sine and cosine. But now that we have this nice and simplified out, we're going to go ahead and try plugging in that limit value again. So when we plug in 0, we get, if we don't exactly remember our trig, this is going to be 1 over sine of pi over 4 times 1 over cosine of pi over 4. So sine and cosine of pi over 4, they're the same value. So we get 1 over root 2 divided by 2 times 1 over root 2 divided by 2. And like I said, when we have 1 over a fraction, we just flip that fraction. So let's go ahead and do that. That becomes 2 over root 2 times 2 over root 2. When we multiply the numerators across, we get 4. Multiply the denominators, we get 2, which is equal to 2. So when we apply direct substitution, this entire limit is just equal to a value of 2. But remember, natural log of y is equal to 2, not just y, the solution itself. So I'm going to make both sides e to the power of that. That way, e and natural log cancel itself out, so we get y is equal to e to the power of 2. So that means our solution, or our actual answer, is going to be e squared. That's how we can use the natural log to evaluate limits as well. Okay, so let's go ahead and see another example. We want to find the derivative of that whole function. So this is another application of logarithmic differentiation. You absolutely could use product rule in this case, but I'm going to show you how a logarithm can make this maybe a bit simpler. So like we always do, I'm going to go ahead and set this equal to y. I rewrote that square root as the power of 1/2, and we're going to go ahead and take the natural log of both sides. So the first rule that we're going to go ahead and use is we're going to use product rule for natural logs. So when we have a product, what we get to do is add those two together. So what I did was I took the first term here and we have the natural log. And then since we're multiplying, what we get to do is we get to add them. And then I took my second term and I have it right. Okay, so our next step is to use the exponent rule. So here we have the exponent of 6 and the exponent of 1/2. And just like we've been doing, those exponents get to come to the front because we're multiplying by them. Okay, so now we have it all separated out using all the log rules that we could use. So we're going to go ahead and take the derivative of both sides in terms of x. So on this left side, we have y in the denominator and y prime in the numerator. And this is equal to 6 times, and we're going to keep doing that same thing. So whatever is inside the logarithm goes on the bottom, and the derivative goes on the top. And then we get plus 1/2. And again, we have another fraction, so we get 7x plus 3x squared minus x cubed. And in the numerator, we get what? 6x minus 3x squared. So of course, we're going to go ahead and multiply this y over because we want to go ahead and get the y prime all by itself. So those cancel out, and here we get y prime is equal to y times, and I'm going to go ahead and simplify this a bit. So 6 times negative 6x squared is negative 36x squared divided by, the numerator doesn't change at all, so we get 6x minus 3x squared. But then the denominator, I can multiply that 2 into everything, so I get 14x plus 6x squared minus 2x cubed. And all of that is multiplied by y. If you don't like writing out this extra step, you think it's unnecessary, you don't have to. You could go straight to this step where you replace y with what it was originally equal to. So here we had y is equal to the original whole problem. So here we have y is equal to the original problem, and I can replace that back in when we multiply it by y. So this is going to be a long one. Okay, like I said, it was going to be a long one. Okay, we get this whole entire thing is going to be our solution. So if you were to set up product rule, you would end up with the same solution. You probably have to simplify it a little bit in order to get here, but this is how we can use logarithms to also get to our solution. So let's try another one of these L'Hopital limit thingies. So notice here that we have the exponent is a variable. So we know we're going to use the natural log. So I'm going to go ahead and set y equal to this. And the purpose of setting y, as we've seen, is to take the natural log of both sides. And of course, we can pull that natural log inside the limit. So another thing, if you're feeling like, I don't want to write out every step, you don't have to. I just write it out for our viewers. But you could go directly to bringing down that power of x and having the natural log of this. So you could go from here directly to here. That's totally fine. I'm just writing out every step so we can see it. So let's go ahead and think about what this is equal to. So when I plug in infinity, here I get infinity times, and this becomes the natural log of 1 because 1 over infinity goes to 0. So that's going to be natural log of 1, which is equal to 0. So this indeterminate form is infinity times 0. But this is not the form that we can use L'Hopital's all. We want to make this look like a fraction, and I have a really cool trick for us to use. So one of these we need to bring to the denominator. So natural log is going to be kind of hard to bring to the denominator, so I'm just going to leave it in the numerator. Now I can bring the x to the denominator, and I can do that by making the exponent negative, right? So I'm just using that exponent rules. I'm going to go ahead and rewrite this again. So I can rewrite x to the power of negative 1 as 1 over x in the denominator. So the purpose of doing this, you will see, when I plug in a value infinity, this becomes natural log of 1 plus 0, which is equal to the natural log of 1, aka this is equal to 0. So now when I plug in infinity over here, 1 over infinity, this is all theoretical, this approaches a value of 0, right? 1 divided by a very large number goes to 0. So that means our denominator is also approaching a value of 0. So here we can see our indeterminate form is going to be 0 over 0. So that's the purpose of rewriting this whole thing, is so we can get it to a form where we can apply L'Hopital's. So let's go ahead and do that. So in the numerator, are you guys ready for this? We have whatever's on the inside goes on the denominator. So 1 plus 1 over x. And now we want to put the derivative of that in the numerator. So what I'm going to go ahead and do, I'm going to write it over on the side. I'm going to rewrite it as 1 plus x to the power of negative 1. So when I take the derivative, I get negative 1x to the power of negative 2, or if you wanted, negative 1 over x squared. So that's what I get in the numerator. Okay, and then all of this is going to be divided by the derivative of 1 over x. So again, I can just rewrite the denominator. 1 over x is equal to x to the power of negative 1. So when I take the derivative, I get negative 1 x to the power of negative 2. Exact same thing, negative 1 over x squared. So that's what I have in the denominator. Okay, we have a lot of fraction action going on. Let's go ahead and rewrite this. So we have the numerator. So the numerator is negative 1 over x squared divided by 1 plus 1 over x. And right now we're dividing by negative 1 over x squared, right? So when we divide, really what we get to do is multiply by the reciprocal. So we multiply by x squared divided by negative 1. So let's go ahead and multiply the numerators and the denominators. So in the numerator, I have negative 1 over x squared times x squared. And in the denominator, I have -1 times 1 plus 1 over x. So let's go ahead and notice the things that cancel out here. First, the negatives cancel out, so I get to ignore that. And second of all, this 1 over x squared times x squared is just equal to 1. So now really what we're working with is, so now let's go ahead and try direct substitution on this right side. So when I plug in that value of infinity, I know 1 over infinity gets really, really small, and it goes to 0. So this becomes 1 over 1 plus 0, which is just equal to 1 divided by 1, which is 1. So I know the right side is equal to 1, but remember, this is still equal to the natural log of y. It's not our final solution, and we're going to do the thing where we have both sides raised to e. That way these cancel out, and we're left with y is equal to e to the power of 1, which is also equal to e. And so this right here is our final solution. So that's all I had for us today. If you enjoyed this video, I have many more like it, so make sure to check out my videos. They're linked down below. Otherwise, keep leaving comments on problems you want to see done, because the more problems you leave is the more I can do for you guys. So if you enjoyed this video, please leave a thumbs up and comment other problems and topics you'd like to see done. Thanks for watching.